In this video, I'm going to talk about the inner product of two vectors. For example, if you have A and B, we will define the concept of inner product, like A dot B, which is also called the dot product. And then we're going to talk about the angle between two vectors. For example, the angle that you see here between A and B, and we try to see what correlation we can find between the inner product of two vectors and the angle between those two vectors. And at the end we get to the concept of orthogonal vectors. So first let's start with the definition of the inner product. Inner product or dot product of two vectors like u and v is a scalar, which means it's a real number, and it's defined as follows: the summation of the products of the corresponding components of the vectors u and v. So that means if u is a vector in a space, in n-dimensional space with n components of u1, u2 all the way to un, and v equals v1, v2 all the way to vn, then we just need to look at the corresponding components. For example, the first component of these two vectors is going to be u1 and v1. The second component is going to be u2 and v2 all the way to the n component, which is going to be un and vn. And then we can say that u dot v, which is the way that we show the inner product or dot product of these two vectors, equals the summation of the products of the corresponding components. So u1 times v1 plus second component u2 times v2 plus all the way to the last component, which is un and vn. Product of these components is going to be un times vn. Now let's look at a very simple example in two-dimensional space. So our vectors are having two components. Vector A has two components. Vector B similarly has two components. So A equals 10i plus 2j, and so that basically means vector A is 10 and 2, and B equals minus half as the first component in x direction, and plus 4, which is the component in y direction. So let's see how we can calculate the dot product of these two vectors. So A dot B is going to be the product of the corresponding components and then summation of those products. So it's going to be 10 times minus half, then addition of that with 2 times 4, which is going to be 10 times minus half, which is going to be minus 5, and the second term is going to be 2 times 4, which is 8. Finally we get 3. So A dot B is going to be 3. So now let's take a look at another example in 3 space. So basically we have a three-dimensional space, so each vector has 3 components. For example, A has a component in x direction, which is 2, in y direction it has 5, and in c direction it has minus 1. So we can then write A in a vector notation like this, 2 and 5 and -1, whereas B equals -1, this component, +1, this component, and +2. So now we have these two vectors, and to calculate the inner product we can just simply say that A equals the summation of the product of the corresponding components. So first components are going to be multiplied by each other, second component, and then third components. So the first component is going to give us the 2 times -1 plus second component is going to be 5 times 1, and finally third component is going to be the product of -1 and +2. So which is going to be the first term is going to be -2, second term is going to be +5, and third term is going to be -2, and we end up with -4 plus 5, which is just +1. So, oops, by the way, this is the A dot B, so let me fix that. So at the end we get A dot B equals 1. Now in this section, now let's talk about the angle between two vectors and how we can calculate that, or we can correlate that with the inner product of those two vectors. Let's say we have vectors A and B shown here, and the angle between these two vectors is shown as theta, and we have this formula here to find the angle between vectors A and B using the dot product of A and B. So basically the formula says that theta equals inner product of A and B divided by the length of A and B, length A times length B. So there is a proof for that. If you are interested in learning how to prove that, please follow the video. If not, you can just skip this section and go to time showing in here. So if you're still here, congratulations, because that means you're curious enough to learn how to prove this relation. So let's see how it works. First, let's write each of the vectors that we have here, A, B, and C, in the vector notation. So, and we consider a general three-dimensional space, so each vector is going to have 3 components. So vector A can be written as A1, A2, and A3. Vector B can be written as B1, B2, and B3, and similarly vector C can be written as C1, C2, and C3. And if we look at these vectors A, B, and C, we can see that they form a triangle, and our goal is to find a correlation between theta and the length of the rest of the vectors A, B, and C. And in order to do that, we can resort to the law of cosines. And the law of cosines simply says that for any given triangle, like what I show here, A, B, and C, with theta being the angle between A and B, C squared equals A squared plus B squared minus 2 times A times B times cosine theta. And this relationship is really useful because we can find a similarity between the triangle that we have shown here and the triangle that is formed by vectors A, B, and C. So if we apply these relationship that we have here from the law of cosines to the triangle that is formed by vectors A, B, and C, then we can write length of C squared equals length of vector A squared plus length of vector B squared minus 2 times length of the vector A, and A and B and C are all vectors, and then times length of the vector B times cosine theta. And now our job is to somehow find the length of the vectors A, B, and C. And what we can do is to go back and look at the schematic that we have here for the vectors A, B, and C, and we can see that vector C is just the vector A minus B. So we can write C equals A minus B, and if you want to make sure this expression is indeed correct, you just can look at this schematic and you can see that B plus C equals A, right? Because if you start moving in the B direction from this point, this initial point, you would end up here, and then if you follow C, then you would end up with this point here, and that would be as if you would have just followed direction A. So A is going to be equal to summation of B and C, and then if you just keep the vector C in the left hand side and send B to the other side, you would end up with C equals A minus B. So this expression is indeed correct, and by having these components for A and B, then you could say that vector C is then the subtraction of B from A. Then the components of C will be A1 minus B1, A2 minus B2, and A3 minus B3. So now let's calculate the length of vectors A, B, and C. So we have 3 components for each vector. We just need to raise each component to power 2, and then we need to add all those terms. Square root of that is going to be the length of each vector. So let's do that. Length squared is going to be the summation of each of the components raised to power 2. So it's going to be A1 squared plus A2 squared plus A3 squared. And similarly for the vector B, we can say that length of B to power 2 is going to be B1 squared plus B2 squared plus B3 squared. And finally for the vector C, we can say that length of C squared equals the first component to power 2, which is going to be A1 minus B1 squared plus A2 minus B2 squared, which is the second term to power 2, and finally the third term raised to power 2, A3 minus B3 to power 2. And if we expand each of these terms, then we will get A1 squared plus B1 squared minus 2 times A1 B1 plus, for the second parentheses, we would get A2 squared plus B2 squared minus 2 times A2 B2, and for the last term we will get A3 squared plus B3 squared minus 2 times A3 B3. So Now we have some appropriate expressions for length of vectors A, B, and C. And now we need to substitute these expressions back into this equation that we have written from the law of cosines. So I have copied all the equations that we have so far here. So the first one is the same that we obtained from the law of cosines, and the second one is just the definition of the length of vector A raised to power 2 and length of B to power 2, and finally for C we have this relationship that we have shown here. So if we substitute A, B, and C length expressions into the first one, we will get, so this whole term is going to be the left hand side of this expression, which is the length of vector C to power 2 from here. And then on the right hand side, the first term is going to be the length of vector A to power 2, which is going to be A1 squared plus A2 squared plus A3 squared. And then the second term is going to be the length of B to power 2, which is going to be plus B1 squared plus B2 squared plus B3 squared. And finally the last term is going to be minus 2. Let's keep this term in the same format. So now let's see, hopefully we can cancel out some of these terms. For example, from the left hand side, A1 squared can be cancelled out with this term. B1 squared can be cancelled out from both sides. A2 squared can be cancelled out from both sides. B2 squared from both sides. A3 squared can be cancelled out from both sides. And similarly, B3 squared can be cancelled out from both sides. So from the left hand side we have minus 2 A1b B1 minus 2 A2b2 minus 2 A3b3. This was the left hand side, and from the right hand side we have just this last term, minus 2 length of A times length of B times cosine theta. Now it's much simpler, and it seems like we have been able to cancel out many of those terms, but it can be simplified even further. If we look at both sides, this factor 2 can be cancelled out from both sides. So from the left hand side we end up with minus A1 B1 plus A2 B2 plus A3 B3, and from the right hand side we will get minus length of A times length of B times cosine theta. So did you notice anything exciting here? Exactly, that's going to be this term, which is going to be just the definition of the inner product A dot B, right? So we can then simplify this expression into I'm going to be cancelling out the minuses from both sides. From the left hand side I'm going to have A dot B, and from the right hand side it's going to be length of A times length of B times cosine theta. And from there it's easy to get the expression that we wanted to prove, because that's simply, that is going to be cosine theta equals inner product of A and B divided by length of A times length of B. So congratulations, now you know where this very famous relationship is coming from. So as an example, let's look at the two vectors that we considered in the previous example, A and B. As before, we want to see if we can find the angle between these two vectors. So A equals, in the vector notation, is going to be equal to 2, 5, and -1. So let's quickly calculate its length. So length squared is going to be first component raised to power 2, second component 5 raised to power 2 plus -1 raised to power 2. So it's going to be 4 plus 25 plus 1, which makes it 30. Similarly, vector B is going to be in the notation form -1 and 1 and 2. So the length squared is going to be first component -1 power 2 plus second component plus 1 power 2, and finally the third component to power 2. From the definition, we know that A dot B over the length of A times length of B, that's going to be equal to cosine theta. So now we need to evaluate the inner product of A and B. So A dot B is going to be the inner product of 2, 5, -1, and -1, 1, and 2. So we just need to look at the corresponding components and multiply those components and then find the summation of all those terms. So 2 and -1. So we're going to get 2 times -1 plus second components 5 and 1, and finally the third component -1 and 2. And if we evaluate this right hand side, we are going to get -2 plus 5 -2, which is going to be +1. So finally we have all those ingredients. We have length of A equals the square root of this term 30. We have length of B equals the square root of this term 6, and we also have inner product of A and B equals 1. Finally, we can go back and calculate cosine theta equals A dot B divided by length of A times length of B, and that's going to be A dot B, which is 1, divided by length of A, which is square root 30, times length B, which is square root 6, and that's going to give us 1 over, and then theta is going to be just arc cosine or cosine inverse of 1 over square root of 180. So finally theta is going to be around 1.496 radian, or in 85.73 degrees. So the last topic that we are going to discuss here is the orthogonal vectors, and that basically means if you have two vectors like U and V in n dimension with n components, basically these vectors are orthogonal if their inner product is 0. So for 2-dimension and 3-dimensional space, this concept has a geometric significance, meaning that when we talk about orthogonal vectors, we literally mean these vectors are perpendicular. So A and B create a right angle in between them. So theta, angle between these two vectors, is 90 degrees. So cosine of theta is going to be 0, And from the definition, you remember that cosine theta was a dot b divided by length of a times length of b, right? So when cosine theta is 0, then that means that a dot b, or inner product of a and b, equals 0. So then we call two vectors to be orthogonal whenever their inner product is 0. And for two-dimensional and three-dimensional spaces, this orthogonal term simply means, or is a synonym of, perpendicular. But for the spaces with a higher dimension, let's say 4-dimension or 5-dimension, etc., there is no really geometric significance for orthogonal concept. We just call those vectors with the inner product of 0 to be orthogonal because they're still going to show some unique properties and behavior that is important for many different applications. So as a recap, we call two vectors orthogonal whenever their inner product equals 0, or vice versa. For example, if two vectors inner product equals 0, then we call those two vectors orthogonal. And now if we have two or three-dimensional spaces, then those vectors are going to be perpendicular. Otherwise, there is no really geometric significance in the term of orthogonal. So as an example, let's take a look at these two vectors, a and b, and we want to see if these vectors are orthogonal. So let's calculate the inner product of a and b. So a dot b equals inner product of 2 and 1 and minus 1 and 2. And then we just need to look at the corresponding components, first components and second components. And we need to find the products of these corresponding components. So the first component is going to give us 2 times minus 1, plus the second component is going to give us 1 times 2. So the first term is going to be minus 2, second term is going to be plus 2. So the answer is going to be 0. That means a dot b equals 0, and from the previous section then we can say that these two vectors are orthogonal and the space is two-dimensional. So that means these vectors are also perpendicular. And in fact, if we draw these two vectors on the coordinate plane, we would get something like this, and we can clearly see that a and b are indeed perpendicular.